Hey guys, Mr. Mills here. Today we're going to look at special right triangles notes. At the end of this video, you should be able to find side lengths in special right triangles, and you should be able to apply relationships of sides in special right triangles. Okay, so this is a great piggyback to our last trig chapter. We're going to look at a couple, just two, right triangles that have some ratios that are pretty consistent enough for us to use without using our trig ratios. So our first special right triangle is a 45, 45, 90 triangle. Okay, we're going to start. It says draw a right triangle with a 45-degree angle. Okay, so I'm going to do that. Boo-doo-boo-boo. Okay, 45-degree angle. Okay, so it says, what is the measure of the other acute angle? Okay, because we have two angles. Well, a triangle has to add up to 180 degrees, 90, 45, 135. So what's left is 45 degrees. Yeah. Besides the right triangle, what type of triangle is this? Okay, so if we know that both of these angles are 45 degrees, this is an isosceles triangle. Isosceles. All right. How do we know? Well, it's the isosceles triangle theorem, right? Or actually the converse of the isosceles triangle theorem, which states that if our base angles of a triangle are congruent, then the angles opposite, or the sides corresponding to those, are congruent. Okay, so how do we know? I guess I can write that down. Converse of isosceles triangle theorem. All right. Okay, so on your calculator, if you type tangent 45, and I'll give you a second to do that, what do you get? Okay, if your calculator is in degrees, you'll get 1. Okay. And recall that the tangent ratio of an angle is opposite side over adjacent side. Okay, and since both legs are congruent, and in this case, I'm going to just call them x here. Call this x. Okay, we don't know what they are, but in all 45, 45, 90 triangles, these two are going to be the same. Since both legs are congruent, our ratio is x over x for this particular triangle, which reduces to 1. Okay. It says now use the Pythagorean theorem to find the length of the hypotenuse in the triangle above. Okay, so in this triangle above, where we have these two sides that we still kind of don't know, we're going to call them x, what would the hypotenuse be? Well, Pythagorean theorem tells us to do a squared plus b squared equals c squared. Just remembering that our legs are a and b, and our hypotenuse is c. So x squared plus x squared equals c squared. 2x squared equals c squared. We have to take the square root of this. And when we take the square root, x has a pair, so it goes out. 2 doesn't have a pair, so it stays in. We see that the hypotenuse is x times radical 2. We'll just write it as x radical 2. Okay, and what that tells us is that the length of the hypotenuse in a 45, 45, 90 triangle is always radical 2 times longer than the length of the other legs. Okay, so now this is what we need to remember. Okay, this when we're asked about a 45, 45, 90 triangle, we're going to need to know these ratios. Okay, x radical 2. This is our 45, 45, 90 triangle. Okay, and as we get values for sides and know them, they won't just be a variable. So let's look at how we'll find those lengths and values in these two examples. So number 1, they tell us that this angle is 45. So we can help ourselves out if we need that extra affirmation here that this is a 45, 45, 90 triangle. Okay, so they're asking us to find BT. These are the legs of our isosceles right triangle. So BT should be the same as AB, which is 8. Then they ask us to find AT. Okay, and now you might be like, oh, I have to use Pythagorean's theorem. No, because it's a 45, 45, 90 triangle, we don't really have to use Pythagorean's theorem because we know that our ratio is going to be x times radical 2. So in this triangle, we know that x is 8, so our hypotenuse will be 8 times radical 2. We could just leave it like that, 8 radical 2. Okay. If directions told you to round to the nearest 10th or 100th, then you could type that into your calculator and get a decimal answer. But for the most part in this chapter, we're going to want to use a simplified radical answer, just because that's how we're going to get our ratios. Okay, number 2, this is a little bit more challenging, asking us to find BO and BY. Okay, this is a 45, 45, 90 triangle. Okay, and so we can help ourselves out and give our ratios like, okay, this has to be x, this has to be x, this has to be x radical 2. Okay, but now we're going from knowing the hypotenuse to finding out what the legs are. And even though it takes more algebra, the setup is pretty much the same. We have basically an equation here. X radical 2 equals 10. Okay, and so we need to find out what x is. How do we do that? Well, we get x by itself. X times radical 2, so we need to divide by radical 2. Okay, and so nice, we got x by itself, but remember that we can't have a radical in the denominator in our final answer. So we have to rationalize that denominator. We can do that by using fancy one. I want to call it that. I know I do, just because. Okay, radical 2 times radical 2 gives us radical 4, which is 2. Then we have 10 radical 2 over 2. We can simplify. Okay, and so then that gives us 5 radical 2. So in this triangle, we find out that x is 5 radical 2. So now that we know that, BO must be 5 radical 2. BY must also be 5 radical 2. All right, great. That is the 45, 45, 90 triangle. Let's look at our second special right triangle, which is 30, 60, 90. Okay, it says in the triangle below, label the shortest side S. S. Okay, so the shortest side has to be S. Now, when we talk about that, remember that we know that the angle corresponds with the side in the sense that the smaller the angle, the shorter the side. Okay, because this angle is 30 degrees and this is 90, then we know that this has to be 60. So based off of that, our shortest side has to be across from our smallest angle. Okay, and so that's how we can identify what our shortest side is in these triangles. Okay, all right. So what we're going to want to do is we're going to prove the other two side lengths, or show the other two side lengths in a triangle. Okay, and I'll kind of prep you this way and say, okay, this is our ratios for 30, 60, 90 triangle. So this is the picture that you're going to want to remember and commit to memory for this chapter. Okay, because we'll use this a lot this chapter, I'm telling you. Okay, let's prove why that's true. Okay, here, as we have this triangle, we're going to start with this 30, 60, 90 triangle. And I want to prove why these values are true. Okay, so the way that I'm going to prove this is I'm going to change this from a 30, 60, 90 triangle. I'm basically going to add to it another 30, 60, 90 triangle. Okay, so what we see here, if I put that together, all these angles, this is 60, this would be 30 and 30, which would make it 60. This is an equilateral triangle. Back to how we started this last time, we said our shortest side was S, right? So this would be S, this would be S. Okay, so as we see here, this side would be 2S. Because it's an equal angular triangle, a regular triangle, equal angular and equilateral. So this is 2S, then that must mean that each side of the triangle must be 2S. Okay, so we have all those triangles, or all those sides figured out. Okay, it's really kind of proof right here for our hypotenuse being 2 times the length of the short side. Okay, and now we need to find I'll just call it our long leg of this triangle. Call it B here. Okay, and so we can find this by using Pythagorean's theorem. Remember, Pythagorean's theorem basically tells us that the two legs squared, the sum of the two legs squared should equal the hypotenuse squared. Okay, so make sure I do that. All right, so I have s squared plus b squared equals, and that gives us 4s squared. To find that other side or prove that other side, we're subtract s squared from both sides, and that gives us b squared equals 3s squared. And we want to find out what that last thing is, so taking the square root, okay, that gives us b. The square root of s squared is s. The square root of 3, we just have to write it as square root 3. Okay, and so proves that that is going to be s radical 3. Okay, so there we go, that's our proof. And because we've used this in just a general sense, right, we didn't have to assign any other values other than knowing this 30, 60, 90 triangle. We have our ratios that are going to be true through all 30, 60, 90 triangles. Okay, so writing this out, just formalizing it here. The length of the hypotenuse, right, is 2 times the length of the short side. The length of the long side is radical 3 times the length of the short side. So notice here that really in the 30, 60, 90 triangle, we want to get back to our short side so that we can find the other lengths of the triangle. Okay, so there are 3 ways that we can do this. Obviously, we can either get the short side, the long side, or the hypotenuse. Okay, no matter what we're given, we need to be able to go to the other 2 sides. So we can solve this, solve for the missing lengths given the short side, obviously, right? The thing that I would say, or I would encourage you to do, is just to make sure that you label your sides first. And I used S here for short, but you can use X or P or T or whatever you want to. I really don't care. And so I know that sometimes when I use S, they're like, oh, is that an S or a 5? You know, I can tell the difference. So if you can't, make sure that you use a different letter. Okay. So here's what I'm doing. I'm just labeling my ratios, basically putting them out there. I know that S is 5. Okay, so if I need to find B, well, that's S 5 times radical 3. 5 radical 3. Okay, S is 5, so C is 2 times S. That's 10. Okay, and so there's our values. Didn't have to take a whole lot of algebra, really, to get from knowing our short side to knowing the other 2 sides. All right, other triangle here. This is my 30, 60, 90. My short side is here. Call it X. I'll call it X radical 3. And I call it 2X. Okay, in this case, I'm using X because it's across my shorter side is already X. I don't know. I don't want to have too many variables that I don't need. I don't know. You can still call it S. The thing that's important is just remembering the ratios. All right, so as we set this up, I know this ratio. So just like last on the 45, 45, 90 triangles, I'm going to set an equation up here and find out what X is. So X radical 3 equals 12 divided by radical 3. Okay, so that gives us X equals 12 over radical 3. Okay, rationalize the denominator. That's 12 radical 3 over 3, which simplifies to 4 radical 3. So now I found out that X is 4 radical 3. All right. Y is 2 times X. So 2 times 4 radical 3. Outside times outside gives me 8 radical 3. All right. And then final example for these notes, we're given the hypotenuse. The hypotenuse in this case is 16. So before I jump the gun, setting this up, this is X. This is X times radical 3. And this is 2X. Okay, so here I have an equation. 2X equals 16. Divided by 2. x equals 8. So now I know that x equals 8. Here, that means this side is 8. Y will be 8 times radical 3, which we'll just write as 8 radical 3. Okay, so there we have it, our two special right triangles, our 45, 45, 90 triangles, and our 30, 60, 90 triangles. Okay, make sure that you're looking at those and remember those ratios because that'll help you out. All right, see ya.